Good day, class. So we will continue with that particular sample problem we discussed last meeting regarding multi-stage leaching. So I'm starting here again just as a review so that we can continue where we left off. So for multi-stage leaching, so you have a series here of, we call this thickeners. This is a particular N thickener, and this is the last N thickener. Um, we have most of the time a pure solvent that is being used in the washings. We have the solids being introduced in the first thickener, and it's being processed in the successive thickeners with the goal of removing the solute present on it. So we want as much as possible to recover 100% of the solute that is present in the original solid feed. Now, what we used as a representation for the concentration of our solvent with the solute is X, and the concentration of our solid concentration is Y. So when we account for the concentration here, again as a review, we don't consider the inert solid. We only account for the presence of the solute A and the solvent C. So we don't account the B in the denominator in the manner in which we express the concentration X and Y. Now, NO specifically represents the concentration of the insoluble solid in our feed in here, the feed LO. And BO is not the concentration of the insoluble solid, but rather the mass of the dry solute-free solid. So just the inert solid is BO. But the concentration of the inert solid is NO. That would be the same representation for the next thickeners. We just change the subscript 0 depending on what particular thickener this N and this B is coming from or is living from. So this is the way we represent our multi-stage leaching in the manner in which the main reference book that we're using, Jan Kuplis, is representing it. Now, when we do material balance for leaching, we can do overall material balance, but we only account for A and C. So that would mean that we need to add the solvent and the feed and equate the sum of the two to the solvent with the recovered solute. And then this one is your slurry, the slurry of the insoluble solid with the solution of the same concentration that is present in your V1. Now we can do as well component balance, and it is suggested that we do the solute component balance in our leaching. So what we have here on the overall material balance in terms of the terms, we simply multiply with the corresponding concentrations X and Y. So as you could see, they were all multiplied to X and Y. Now, for an agitator and washing system, so we also have a solid that is continuously being washed. So it's being washed with a pure solvent, or it's referred also to a fresh solvent. So the manner in which we represent our thickeners here is based on where our solid is introduced. So if our fresh solid is being introduced in this particular thickener, then this is our thickener 1, and this would be our thickener 2, and this would be our thickener 3. So that's where our solid is being introduced. So our solvent is numbered based on the particular thickener in which it is coming from. So in the case of this one, since this is your thickener number 3, if I may call it the thickener number 3, then this particular fresh solvent will have a subscript of 4, because this is understood to be coming from the thickener number 4. Okay, so this is how we represent our agitator washing system, a system in which our solid is being continuously washed by our solvent to recover the solute that is present on it. So this is our washing system. And this is where our next problem will be based on. We have an agitator washing system with the goal of removing the solute that remains in our inert insoluble solid B. Okay, that is present, both being present in our feed. Now, this is the problem that we've worked out last time. So the caustic soda, which is being manufactured by the lime soda process, and that this particular solution of sodium carbonate in water contains 0.25 kilograms per second of sodium carbonate, and it's being treated with the theoretical requirement of lime. So as for it to be able to produce the caustic soda and the calcium carbonate. So our leaching process wishes to address the remaining amount of caustic soda that may be adhering on our calcium carbonate solid, since our solid is in the form of a sludge. Now, this calcium carbonate contains 1 part calcium carbonate and 9 parts water. Okay, it's being fed continuously to 3 thickeners, as could be seen here, and washed countercurrently. So you are asked to determine the necessary amount of the feed water, or that's the amount of our wash solvent. It is to be assumed that this particular solvent is 100% pure, meaning no other components present on it. And then we have this added information that the solid as discharged from each of the thickeners contain 1 part by mass calcium carbonate to 3 parts water. So this particular ratio is by mass. Even if it's not written here by mass, but when we speak of parts, we're referring to the unit in mass. So since it is being stated here that the solid that is being discharged in each thickener is containing 1 part by mass calcium carbonate to 3 parts of water, it is to be correctly assumed as well that this particular ratio is a constant to all of our thickeners. Because if our amount of calcium carbonate present is varying, with in terms of the amount of water that it is present with, or that is with it in the slurry, then we have a case of variable underflow. In this case, it's fixed to be 1 part calcium carbonate and 3 parts water. So for all thickeners, that would be the relationship between CaCO3, or calcium carbonate, and water. So the end goal for this problem is we will find the amount of the wash water. And if you may recall, and if you have already watched the previous discussion on this, recorded discussion on this, we already solved for the x sub 3. What is this x sub 3 prime? So that would be the mass ratio. The mass ratio of the solute, which is our caustic soda, the sodium hydroxide, and the solvent, which is water. Okay, it's the mass ratio. The reason why it has the prime in this particular problem is it's not the usual way we express concentration in leaching. So if you recall, in the primary principle for leaching, we express concentration in terms of solute over solute plus solvent. In this case, since our X has a prime, it's only solute over solvent, not solute over the sum of the solute and the solvent. So that is why here you could see that you have the primes in the excess. Without the primes, and if these excess are written in capital letter, then we will have the usual interpretation of the manner of expressing concentration for leaching. And that is solute over solution. Okay? This one is solute over the solvent. So going back to what I have stated a while ago, last meeting, we have ended with the corresponding amount of x sub 3 prime out of making. So if you may recall, we made an overall material balance. You made an overall material balance on our system for each of the 3 components in our, shall we say, chemical reaction or stoichiometric equation. We accounted individually for calcium carbonate, our caustic soda, that is the sodium hydroxide, and for the water. Now, you may wonder why was there no, shall we say, component balance based on the lime, that is the calcium hydroxide. There's no need for us to make a component balance on the calcium hydroxide. This was also stated in the previous discussion because it was stated here in the second line that our calcium hydroxide is in the theoretical requirement. So meaning whatever is required, that is the amount of lime that was used in the process. And there's no need for us to account for it because we only need to account for the solid, the calcium carbonate, the solute, which is our caustic soda, and the solvent, which is our, of course, water. So we made a material balance, an overall material balance based on these three components. So I say overall material balance because it's based on the entire system. Although it's not overall material balance in that sense in the way we view it with the other separation processes because we're not adding everything up, but rather we're just accounting individually for these three components, but on the whole system, not on each of the thickeners. After we're done making an overall material balance based on those three components mentioned, we did a material balance on each of the thickeners after that. So the material balance was also based on the three components: calcium carbonate, sodium hydroxide, and water. Now, we ended last meeting with the computation of the x sub 3 prime based on the fact that after drying, so after this wash product here leaves your third thickener, this wash product is introduced into a dryer. And after drying, it was mentioned that your calcium carbonate is left with 1% sodium hydroxide. So last meeting, we made use of that 1% of sodium hydroxide and the overall material balance based on sodium hydroxide to determine the value of x sub 3 prime. And the value of that x sub 3 prime was already given in our previous recording to have a value of 0.00337. So our goal for this afternoon is to finish the solution of this particular problem and go with the next topic on leaching. And that is also very important. That is analytically determining the number of thickeners or the number of stages for a particular leaching process. Okay? Now, since we know already the x sub 3 prime, the next thing that we need to do, of course, is we should know this x sub 1 prime and this x sub 2 prime. Okay, let me annotate. So we already know this one. So the remaining things that we need to know are these two: the x sub 1 prime and the x sub 2 prime. We need to know the x sub 1 prime and the x sub 2 prime. That way, if we have representations of these two, it may lead us to the amount of the wash water here, which we're looking for. This is the S prime that we were looking for in this particular problem, the S. So we cannot solve for this S unless you determine the x sub 1 prime and the x sub 2 prime. Not specifically maybe determining their values, actual values, but only an expression of these two that would lead us to manipulating or working on a system of equations that would lead us to determining the S. What do I mean is, it's not necessary that you know the actual value, numerical value of these two. Only that we will use the representation of these two expressions in a series of equation. That way we can find the S. Okay, now we've learned from leaching that the concentration of the solute, in the case of this problem, our solute is the sodium hydroxide or the caustic soda. We know that it's a primary principle in leaching that the concentration of the solute in the underflow is equal to the concentration of the solute in the overflow, in whatever form of representation that particular concentration may be. What do I mean by that? So if you have x sub 3 prime as the concentration of the solution in the underflow of this third thickener, meaning this one here, is x sub 3 prime, it follows that the concentration here of the wash water is also x sub 3 prime. These two are to be equal based on the concept of leaching, that the solution that adheres to your insoluble solid in the slurry will have the same concentration as the solution that is present in the overflow. That's the primary principle of leaching. So we will use that particular representation. That way we can have three working equations. Three working equations with four unknowns. Three working equation with four unknowns, which I will show to you a while ago. The four unknowns includes x sub 1 prime, x sub 2 prime, x sub 3 prime, and s. But since we know already the x sub 3 prime, then we of course can solve for these three, knowing that we have three equations to use. So three equations with three unknowns, of course, would lead us to whatever unknown we want to solve. In this case, we are interested in the S. So we're interested on the S. So now we'll go to the representation of the concentration of the underflow for thickener 1. And for us to be able to do that, of course, we need to go back to our board. Okay, so for thickener 1, we have the concentration of the underflow being equal to, remember that this concentration is solute over solvent only. Now, based on the table that we had, if you already listened to the discussion, the previous discussion, which is also tabular in terms of the representation of the amount of the solute and the solvent in thickener 1, our solute, that is our sodium hydroxide in the underflow of thickener 1 is 80 minus 300 x sub 3 prime. You can get this from the previous recording, or it would help that you also, when you listen to the recording, you write this down so that you can go back to the solution later on and connect the two. So this is the solute present in the slurry of your thickener 1. We will divide it to the solvent present on it, which is 600 plus S. So in here, you could see that you have x sub 3 prime, and you can actually substitute the x sub 3 prime here. So if you will substitute, you will have 80 minus 300, and then you multiply it with the x sub 3 prime that we have solved already. Oh, there is another 3 here. And you have 600 plus S. Okay? In here, we can get an x sub 1 prime equal to 78.989. So you can redo the computation. We divide it by 600 plus S. So we will make this as our equation 1. So if you will start with equation 1, that's our equation 1. We do the same with the representation for the concentration of the underflow. So for thickener 2 this time. So again, it's still solute over solvent. So for thickener 2, we have 300. Sorry about that. 300 to be multiplied to the quantity x sub 1 prime minus x sub 3 prime, and we divide it with the amount of solvent present in thickener 2, and this would be our equation. Then we can substitute the x sub 3 prime that we already determined. So x sub 1 prime minus 0.00337, and we divide by S. Now, in here, you can have an equation of x sub 2 prime in terms of S, just like you have here x sub 1 prime in terms of S. So, x sub 2 prime in terms of S would be 300 x sub 1 prime minus 1.011 divided by s. We will make this as our equation 2. Okay, let me pause for a while so I can... Now we have T sub 1 and T sub 2 accounting for the concentration or writing down the concentration expression. We can do that also for thickener 3. So for thickener 3, we have x sub 3 prime, and we have for that 300 times the quantity x sub 2 prime minus x sub 3 prime divided by thickener 3, that would be S. So the only difference between this one and this one is x sub 1 prime. This one is x sub 2 prime. If we will substitute the value of the x sub 3 prime that we have, which is 0.00337 divided by S, we also have a representation for x sub 3 prime in terms of S. And that is okay. So you will have here a 300 x sub 2 prime minus, so you can multiply this two. That would be your 1.011 all over S. So you have now 3 equations with all the S present. So you have equation 1, 2, and 3. Now, in here, you could see that in your x sub 2, for you to be able to find the S is for you to substitute the x sub 1. And once you have the x sub 2 already done in terms of the representation, in terms of S, then this x sub 2 prime will be substituted in here. So what do we mean? So we will plot our course here. So we will place here. So I will not have to write the solution. You can do that as an exercise. We substitute 1 to 2. So, okay, I'll show to you. So we substitute equation 1, the x sub 1 prime, to equation 2. Then we substitute equation 2, which is now x sub 2 prime in terms of S, to equation 3. So I'll place here substitute 1 to 2, then resulting expression, this one, substitute to 3. Now, if you do that, you have eliminated x sub 1, you have eliminated x sub 2, and in here in x sub 3, you know already the value of the x sub 3 because we have determined it. That would leave you to determining the S. Okay, so you can have the S value. Now, I will just simply place the S value. That way we can save time. So your S value, if you compute for it, is 977.0253 kilograms. Now, take note, kilograms per second. Take note that this one is 4, so we started with 100 kilogram or kilograms per second of calcium carbonate because this is the theoretical amount that will react with your lime to produce your caustic soda, which is 80 kilograms per second, and your calcium carbonate, which is 100, okay, wait, 100 kilograms. Yeah. And will actually, it's your calcium carbonate, which is 100 kilograms, but your original feed, which is your sodium carbonate, would be 106 kilograms per second. Okay? Now, we need to determine then the amount of the S. This is not yet the S that we're looking for. We need to determine the amount of S for the sodium carbonate, which is only 0.25 kilograms per second. Remember that as stated, this is for 100 kilograms per second of calcium carbonate for a feed of 106 kilogram per second sodium carbonate. So this is your solid produced if this is the theoretical amount of sodium carbonate that was processed. These are all theoretical. The actual that is given in the problem is only 0.25 kilograms per second of sodium carbonate. So now considering the actual for 0.25 kilograms per second of sodium carbonate, you need to account for the corresponding amount of calcium carbonate that will be produced. Okay? How much calcium carbonate will be produced for using only 0.25 kilograms per second sodium carbonate, because this one used 106 kilograms per second sodium carbonate to produce this much of calcium carbonate, which is 100 kilograms per second. So we will do that. So the kilogram of calcium carbonate per second that is produced out of the 0.25 kilograms per second of sodium carbonate can be solved using, of course, stoichiometric relationships. So we first convert the kilograms here to mole. So 106 kilogram sodium carbonate per 1 kilomole sodium carbonate. Then we will have 1 kilomole sodium carbonate to 1, or based on our stoichiometric relationship, this could also be mole. So 1 mole of calcium carbonate. It's okay whether it's kilomole or mole. So we cancel this, cancel this, cancel this, we cancel this. This is already kilomole calcium carbonate, and we only need to multiply here with the molecular weight of calcium carbonate. So kilogram calcium carbonate to kilomole calcium carbonate. So we cancel this. So in here, we'll be able to get the amount of only very small, 0.2358 kilogram per second calcium carbonate. So if you have only processed this much of feed, this is only the solid amount that you will produce. But since the solid that we use is 100, so we need to find by ratio and proportion the corresponding amount of the S for just this much of calcium carbonate. So by ratio and proportion, we can have the S to calcium carbonate process. So if we'll have the 977, this is our computed amount of S needed based on the theoretical amount of calcium carbonate produced. You need not write the units. Then what would be the corresponding S that will be produced if we will only have as much as 0.2358 of calcium carbonate. So this is calcium carbonate, this is calcium carbonate, this is S based on this amount of calcium carbonate, and this is S for this amount of calcium carbonate. Therefore, the amount of wash water that we'll be using here is 2.3 kilograms per second. So this is the answer to our problem. The only way that we found this answer, or we're able to determine the answer, is by using overall material balance and individual material balances for each of the thickeners. And we made use of the principle, the very important principle that was used here is this one. Concentration in the underflow is equal to the concentration of the solution in the overflow. So this is our representation for that. So this is our concentrations for the three thickeners, and we solve the three equations simultaneously to find for the S. Okay? Now, there's a note that if you're going to actually process the three equations here, 1, 2, and 3, you will come up with an equation which is a third degree polynomial in S. So meaning before you can reach this one, you will have an equation which is a third degree polynomial in S. If it's a third degree equation in the polynomial S, you can use Newton-Raphson, that method that you have learned in your advanced engineering mathematics. For determining the roots of equations. So you have to turn your equation first into a form in which the right side is set to 0. Then you use Newton-Raphson to find the value of S. That way, you will be able to correctly determine the S, the wash water needed for this much of solid that will be processed by your thickeners. I'm not sure though if your calculators can directly solve the S value for a third degree polynomial without having to start from a certain initial incremental value, because what we do with numerical methods is we do iterations until such time our current answer will be more or less comparable to or equal to the previous. So that's what we do when we iterate. So I think I need not explain it here because you have already fully covered that in your advanced math. So if you will do this later on by yourselves, please check on the method of Newton-Raphson if your calculators cannot solve for the value of the variable for a polynomial of degree higher than 2. I know it can give you the roots for a quadratic equation, but I'm not certain if it can find the roots for higher degree polynomials without having to start with a starting value to use in the iteration. Okay, so this is the end. This is the solution for our sample problem number 3. Now we're ready to go to a new topic in leaching, which is actually finding or solving for the number of stages. Now what I'll do in solving for the number of stages is I will have a separate recording for that. That way when I have this uploaded, it will not be too long, that it will take some time to upload because I need to have it rendered first. So I will stop here and then have a separate recording on the last topic on leaching.